In the late 1950s, the arms race between the United States and the Soviet Union reached a fever pitch. Both nations were pouring billions into finding a weapon so fast and so relentless that no defense grid on Earth could intercept it. The U.S. Air Force believed they found the answer with Project Pluto. Their objective was to build the Supersonic Low Altitude Missile, commonly referred to as SLAM. This diagram shows exactly how they planned to do it. On the left, a standard turbojet engine compresses incoming air, mixes it with chemical fuel, and ignites it to create thrust. On the right, the nuclear ramjet replaces the combustion chamber entirely. Instead of burning fuel, the incoming air is rammed at high speed directly through the glowing, unshielded core of a nuclear reactor. The reactor instantly flash heats the air to over 2,500 degrees Fahrenheit, causing it to violently expand out the rear nozzle to generate continuous propulsion. Because a nuclear reactor can operate for years on a single load of highly enriched uranium, the missile didn't need heavy, finite fuel tanks. This propulsion system gave the SLAM a theoretical range of roughly 113,000 miles. It could circle the Earth's equator more than 4 times before running out of power. By harnessing nuclear fission for propulsion, the engineers at Project Pluto had inadvertently built an engine that weaponized its own flight path. The SLAM was designed to loiter in the sky for weeks. Upon receiving an attack order, the missile's payload bay would sequentially eject up to 26 individual thermonuclear warheads over different enemy targets. But the bombs were only the first layer of destruction. To evade radar, the missile would fly at Mach 3, just 1,000 feet above the ground. At that speed, the resulting 162 decibel sonic boom creates a shockwave powerful enough to flatten unreinforced structures and kill anyone directly beneath its path. The propulsion system itself constituted a third weapon. Because the Tory reactor utilized an open core design with absolutely no radiation shielding, the intense heat and pressure from the passing air would gradually ablate the reactor material. The missile would continuously blast highly radioactive fission fragments, including deadly isotopes like strontium-90 and cesium-137, straight out of its exhaust nozzle. As it navigated across the globe, the SLAM would lay down a wide, invisible trail of lethal nuclear fallout. It would silently poison thousands of miles of land, water, and civilian populations long after the missile had flown by. After dispensing its final warhead, the missile had no landing gear and no recovery protocol. Its final program directive was to execute a terminal Mach 3 dive directly into the ground. The kinetic impact would shatter the airframe and violently rupture the unshielded reactor core, turning the crash site into a permanently contaminated wasteland. Even without dropping a single bomb, the SLAM would inflict catastrophic environmental and structural damage across an entire continent. Making this theoretical machine a reality fell to the Lawrence Radiation Laboratory. They faced a severe engineering bottleneck, building a reactor light enough to fly, yet durable enough to withstand 2,500 degrees Fahrenheit. Standard high-strength metal alloys would instantly melt under those conditions. To solve the heat problem, engineers discarded metal internal parts completely. Instead, they fabricated the core from nearly 500,000 highly enriched hollow hexagonal ceramic fuel elements manufactured by the core's porcelain company. With a viable reactor design in hand, the team needed a place to test it. Because the engine intentionally spewed radiation into the open air, the military established Area 401 at Jackass Flats, deep within the remote Nevada test site. To simulate the massive airflow of a Mach 3 flight without actually launching the missile, the testing facility required extraordinary infrastructure. Engineers constructed 25 miles of interconnected oil well casings to store 1.2 million pounds of highly pressurized air, which would be blasted straight into the reactor's intake. The program culminated on May 20, 1964. Locked onto a specialized railcar, the massive valves from the tank farm opened, feeding 410 pounds of air per second into the full-scale Tory 2C reactor. The reactor successfully reached criticality. For nearly 5 continuous minutes, the Tory 2C generated over 500 megawatts of thermal power and 35,000 pounds of thrust, significantly more power than a modern F-16 fighter jet. The ceramic fuel tubes held together perfectly under the extreme pressure and heat. The Jackass Flats ground runs proved that the physics were sound. The United States now possessed a fully functional, nuclear-powered suicide engine. Yet on July 1, 1964, just weeks after the flawless Tory 2C full power test, And with $260 million already spent, the Pentagon abruptly canceled Project Pluto. Under the leadership of Defense Secretary Robert McNamara, the strategic calculus had shifted. Intercontinental ballistic missiles, like the solid-fueled Minuteman rockets, had matured into highly reliable delivery systems. An ICBM could cross the globe and strike a target in 30 minutes, whereas the SLAM would take hours. Ballistic missiles were simply faster, cheaper, and far cleaner. Beyond budget logistics, there was a severe practical limitation. The SLAM was physically untestable in flight. Launching the missile meant subjecting whatever territory it flew over, whether the open ocean or allied nations, to a deliberate radiological disaster. The program achieved every technical milestone it set out to conquer, but by perfecting a machine designed to annihilate everything in its flight path, the engineers had created a weapon too indiscriminate to ever be deployed. Today, the remnants of Site 401 remain isolated in the Nevada desert. The rusted heavy-duty railroad tracks, the decaying disassembly bunkers, and a 6,300 square meter radioactive leach field serve as monuments to the darkest impulses of Cold War engineering. The concept, however, did not stay buried in Nevada. In 2018, Russian President Vladimir Putin announced the development of the 9M730 Burevestnik, known to NATO as Skyfall. It is a modern attempt to build a nuclear-powered cruise missile with a nearly unlimited range. The catastrophic risks of flying an unshielded nuclear reactor remain unchanged. In 2019, a recovery operation for a sunken Russian test missile in the White Sea resulted in a massive explosion, killing at least 5 scientists and causing a sharp spike in regional radiation. The constraints that kept the Doomsday machines of the 1960s on the drawing board relied on a fragile strategic balance. The revival of nuclear ramjet technology suggests that the lines between deterrence and total devastation are thinning once again. If you found this history compelling, make sure to subscribe to Archive World. Let us know in the comments below. Do you think the catastrophic risks of nuclear-powered missiles will ultimately keep them grounded?